I've actually thought about that. Very excited for our Q-Farm seminar speaker today. So Aashish studied physics in Toronto. He graduated, went to Cornell, did his PhD there.
That is right, yeah.
And to Yale, working in the theory group with people like Urban. So he's had a great influence on one working on hardware. This paper on measurement and required reading for anyone who's trying to build stuff and understand quantum measurement works lab. Since after his postdoc, he started at Yale and was there for 15 years.
A little bit less, but
okay. And then went off to University of Chicago, where he's currently
PMD now.
Yeah. Okay.
My change again.
Yeah. Okay. And he's won all sorts of awards, including the Sloan Fellowship, Simon Rutherford. Okay, so I'll not embarrass myself.
Great. Thanks a lot, Amir, for the introduction and for the invitation to come here. I think the last time I gave a talk at Stanford was a while ago, so I'm definitely happy to do that. It's already been fun to have some fun conversations this morning. Cool. So the title of this talk might sound daunting: Hidden Time Reversal Symmetry Back Solutions of Driven-Dissipative. Actually, spin models will have things beyond spins as well. I'm going to tell you about a line of work in my group that's been going on now for a couple of years, where we're interested in complicated quantum systems that are subject to driving and dissipation. We want to say things about these systems, but we want to say exact things. We don't want to use approximate techniques, whether it's perturbation theory or field theory or some fancy numeric. And the kinds of systems we're interested in are the kinds of systems hopefully many of you are interested in doing experiments on. So systems of interacting qubits, interacting photons, even fermionic systems. And again, we're interested in these systems in regimes that seem complicated. The interactions or nonlinearity are strong. You may be really in some kind of many-body limits. Okay. And the way we sort of found an approach that lets us say exact statements about these systems is to almost think about something that seems completely unrelated. It almost sounds like philosophical. How do I think about time reversal symmetry in an open quantum system? What I'm trying to convince you is there is a very funny, weird notion, something we call hidden time reversal symmetry, that's actually applicable to a lot of the kinds of physical models I'll tell you about. You can think of it as that kind of quantum version of detailed balance. If this symmetry exists, it gives you a really efficient way to say exact things about these systems. So I'll try to give a gentle introduction to what this idea is, what I mean by hidden time reversal symmetry. How do we use it to actually get insights into these different systems? And then also tell you a bit about the physics. Right? So with these exact solutions, we don't just write them down and go, hey, I'm excited to have an exact solution. We can learn things about these models that might be very, very difficult to just get out of, let's say, brute force. Okay, and let me just start by really making sure I acknowledge the people who actually did the work. So again, this has been going on in my group for a number of years. It really got started with a former student, now David Roberts, who was sort of instrumental in building up the main ideas here. Assisted by Andrew Lingenfelter, who's a current PhD student in my group. And then we've had a lot of fun just using these techniques for different kinds of systems. So the thing I hope to tell you about at the end, a kind of interacting spin chain model where we can say exact things. That's involved 3 students in my group. So Jeffrey, Andrew, and Aashish. Okay, so let me start with like a big picture motivation for what we're interested in. So I'm a theorist. I am interested in basic physics depicted by this cartoon. So I have a quantum system. It might be complicated already to begin with. So it has some Hamiltonian that could be describing many interacting particles. I'm going to make life more interesting and more complicated. I'm going to drive the system. The driving could come in the form of making the Hamiltonian time dependent. It could come in the form of adding terms that can add and remove particles, right, from the system. And then I'm going to balance that driving in some way by having some dissipation, some way for energy to relax in the system, some way for maybe particles to sort of leak out of the system. Again, a general question, there's many things you could ask about this. What is the ultimate interplay of all these ingredients? Complicated Hamiltonian, some driving that is putting excitations in, that driving is balanced by dissipation. Okay, so of course, this is just a very, very simplistic PowerPoint cartoon. This kind of physics is relevant in all sorts of places of experimental relevance. You could argue almost any experiment in quantum information physics has elements of that cartoon in it. Here are some examples of just recent experiments where people are really trying to explore this physics as maybe a source of new kinds of interesting many-body phenomena. Okay, so here, for example, is a really nice, very recent experiment from Antoine Brouet's group, where the system of interest, if you turn good eyes, you can see there's a cloud of rubidium atoms here. They are driven with laser light. And the way that these atoms decay, there's something collective about their spontaneous emission. So there's very, very old predictions that say this kind of system can have an interesting kind of dissipative phase transition. This experiment shows evidence of seeing that transition. This experiment has also prompted many other theory papers that say maybe the transition isn't what they first thought it is. But again, this is an example of this interplay giving you something like a dissipative phase transition. Here's a very, very different recent experiment, a different kind of system. So this is from the Google Superconducting Quantum Information Group. This is an array of transmon qubits. And this array of transmon qubits is trying to mimic the physics of a 1D driven chain. So excitations can pop in this chain. They've engineered things in a way that you're pumping excitations in on the first qubit, excitations are leaving on the last qubit. You're interested in how are excitations flowing through this system, right? How is that complicated by the interacting nature of the quantum dynamics? And possibly disorder. So it's really, really interesting non-equilibrium quantum physics that you can kind of study in this sort of platform. Okay, so certainly there are experiments probing just the fundamental things that come out of this interplay. This kind of cartoon is also something that maybe you want to realize in a controllable way to do something useful for quantum. So if you think about a system where you can actually tailor the kind of driving and dissipation the system sees, this is a nice resource for preparing interesting quantum states. It's the whole idea of what people call quantum reservoir engineering. Taken to its extreme, right, this is a way of even trying to do an autonomous form of quantum error correction. Okay, so here's a nice experiment from maybe 2 years ago from Ken Wang's group at UMass Amherst. The idea is to realize some dissipative quantum dynamics by having some clever drives and dissipation. This is a superconducting quantum circuit where you can actually stabilize a logical qubit. So the logical qubit here lives in a photonic resonator. The logical states are superpositions of different clock states, right? You can have loss in this system, right? The idea is to design some driving and dissipation that kind of undoes the effect of loss and preserves the quantum information. Okay, so all of this is to say, there are good reasons to try to understand this kind of cartoon in situations where the physics is complicated. Let's go back to the original question I posed. We would like ways of trying to describe this interplay exactly, right? Without making resource to approximations. In regime for the physics is, at first glance, complicated looking. Okay, and what gives us some hope that this might even be possible? We know if there was no driving and dissipation, there are closed systems with no dissipation, where naively they look strongly interacting, but you can get exact solutions, right? This is the field of integrable quantum systems, the field of Beta-Ansatz techniques. So you could think that what we're trying to do in some way is there something spiritually similar to these amazing techniques from integrability that could give exact insights into this process. And so spoiler alert, I'm not going to tell you about a dissipative or non-Hermitian version of the beta onset. And then I tell you something else that has something qualitatively similar. There's a very funny kind of hidden symmetry in a lot of the systems described by this cartoon that lets us say exact things. And throughout this talk, there's many questions I could ask about this system. I'm going to really focus on one particular question. What is the steady state of the dynamic? So the system is described by some density matrix. At long times, it will relax into some state that involves balancing all these three ingredients. Can I describe that state completely? Okay, that's going to be the state. Okay, and so just the setting for everything I'll tell you about. The setting is there's a system, it's coupled to an environment. The environment is always going to be Markovian. Okay, I'm always going to be describing my system with this GKSL or Lindblad style master equation. So this is the density matrix, the reduced density matrix just of the system. My evolution equation here, in case you haven't seen this before, this is just evolution from the system Hamiltonian. All the effects of dissipation are covered by this dissipative superoperator, right, acting on the density matrix. You can think of these different terms here as describing the different ways dissipation could affect the dynamics of my system. Okay, I want driving as well, not just dissipation. I'm always going to focus in this talk on the driving being describable in the rotating wave approximation. So my Hamiltonian is never going to be time dependent. Describe some, I don't know, oscillating microwave voltage or laser field. The driving is going to show up in terms of the Hamiltonian. It can add and remove excitations. So just to be concrete, here are two kind of simple examples of driven dissipative problems in this framework. So this is how I would describe a single qubit that has a Rabi drive that has some T1 decay. So the dissipation is Z operator is just sigma minus the qubit lowering operator. The Hamiltonian in the rotating frame, this omega, this sigma X term, that's my drive. The delta is the detuning. Okay. Let's take a bosonic example. This would describe a photonic cavity that is subject to a 2-photon or a parametric drive. I'm adding and removing photons 2 at a time. Again, no explicit time dependence. And now the loss, the dissipation, corresponds to removing the photon. There should be no minus over there. Okay, so these are like simple single qubit, single cavity examples of this, right? I want things that are not simple. So let's try to think about taking these simple examples in general. Okay. So I talked about like a 2-photon driven cavity. What if I have many cavities, right? So AI here is the lowering operator of the I cavity. I have some very generalized 2-photon driving. You can call this pairing if you want to use condensed matter language. You can add 2 photons on a given cavity, on any 2 kind of cavities, right? I have some interactions, right? So some Hubbard or like Kerr type interactions. And maybe I can balance that with this loss, okay? This U is maybe not small, driving is strong, not an obviously trivial problem. What is the dissipative steady state of this system? And this kind of setup is relevant to experiments in superconducting circuits. It's also very close to the ingredients you use to build what people call a coherent Ising machine. Okay, so here's one kind of complicated looking system. What about a complicated system involving spins? Well, what about a setup that really corresponds to a lot of the ingredients in that Antoine Brouet's experiment? So here's now some collection of qubits in 1/2, right? The qubits are interacting with one another via Ising interactions. Here I put them to be all to all, so Z-Z interaction between the different qubits. And every qubit now is undergoing this kind of Rabi driving, right? So every qubit, omega sub j, is the amplitude of the Rabi drive on qubit j. Okay, and again, this is relevant to that experiment I showed you from Antoine Brouet's group. It's relevant to other experiments that are going on. Not an obviously trivial problem, right? What would the dissipative steady state of this kind of setup be? Okay, and then how about an example that is maybe closer to that Google experiment that I talked about? So here is also a system just involving qubits, spin 1/2. This is now supposed to, let's just look at one of these chains. This is the spin chain, right? Where I have driving maybe just on site 1 of this n-site spin chain. Again, this X field is the Rabi drive. And maybe excitations can hop, and maybe I throw some interactions there. Okay, so 3 hopefully very different looking systems that have these elements of driving, dissipation, interactions, and nonlinearity in some way. 3 systems that just staring at them don't look obviously trivial or solvable. They also don't look necessarily like they're related to one another. If you have a great idea for how to solve this, it's not clear, it's going to help you with panels 2 and 3. And so the kind of fun story I want to tell you is all of these things are exactly solvable. Like there's a way of analytically describing the dissipative steady state of all 3 of these models without making any further approximations. And also the way that we get solutions for all 3 of these models, there's a common technique. Okay? And this common technique is thinking about a funny notion of universal symmetry that exists in all of these models. This thing that I call hidden universal symmetry. Okay, so my plan for the rest of the talk is to first take a bit of a detour and build up this idea of hidden universal symmetry. And then once we have some idea of what the definition is, just use it to tell you about maybe 2 or maybe all 3 of these different classes of models we can describe this. I should also say I'm more than happy to take questions.
Yeah, so I say for the Ising model, it's all constant.
It's all to all here, and that's you can save the question as to whether it needs to be all to all to still have these solutions for it, right? Any other questions at this stage? Yep.
Just wondering, like, I know like these systems you separate them by like spin or boson, but like what if we have like at each side we have both spin and bosons? Like can these still apply?
So I think one has to be an optimist being in science. So we have a technique that works just for bosons, just for spins, even systems that are not collective. I strongly suspect this technique will also work for mixed systems like what we described. We haven't done that explicitly, but I would be shocked if I couldn't come up with an example that sort of works. I also want to make one thing clear. I'm not claiming the technique I'm going to tell you solves everything, right? That would be disturbing to have someone tell you that. I am saying, though, there's a wide class of systems that have this funny symmetry that we can make exact statements about. Okay, so that might be disappointing to some of you, but it might be exciting to some of you that there's a lot of systems we can make these statements about. Is there a question there?
Yeah, I'm just wondering if you just have a generic time independent system, usually how we set, so the steady state confining is some kind of thermal state. You just, from your technique, would you be able to like find anything?
No, it's actually like, and I'm going to make this more precise. Those are systems that I'm going to define as being boring, right? And it's boring because a thermal state would be like, I know the Hamiltonian and I know the temperature, that's it, right? There's not really much more you need to know about the steady state besides the temperature. The steady states I'm interested in, simply knowing the Hamiltonian doesn't let you understand the full operator structure steady state. So that's going to be a much more interesting non-equilibrium steady state. Those are the things we're going to want to target. Yeah, good question.
Just following up on the question, these states are not thermal states after in the static state.
They will not. I haven't told you what they are, right?
So
you'll find them. But we are going to find exact solutions for all of these. None of them are thermal states in the sense of being an exponential of minus the Hamiltonian of the system divided by temperature, right? So formally, the logarithm of the steady state density matrix will not be the Hamiltonian that generates the dynamics. Yeah. And maybe when I give you an example, it'll be a bit clearer of how these things are useful.
I guess I need to finish my question is that because these systems are having a lot of symmetry, not the hidden time reversal symmetry, but some more practical symmetry.
So just think about like a driven harmonic oscillator, right? So the steady state that you basically get comes from the balance of I'm driving this thing with a force, it's balanced by dissipation. That steady state is not a thermal state, right? So it's the same thing here. The reason you're not getting simple thermal states is what is actually determining this final state. It's balancing the way energy comes in. I haven't drawn it here, but the way that the energy is moving out. Sometimes that gives you still a thermal state. Sometimes it doesn't. Maybe we'll pick up a concrete example will be a bit clearer. You're going to put me off from make sure I don't talk about time reversal symmetry, but that's the next thing we're going to do. Okay, so let's push forward. Okay, so to be able to say sort of exact things, we need to sort of understand something about time reversal symmetry. That is the hammer I'm going to use as a tool to sort of understand these systems. So quick primer on things you hopefully already know about time reversal symmetry. If there's no dissipation, classically, we solve the equations of motion. If I play the movie backwards, I flip momentum minus p, that's still a good solution. Quantum mechanically, if I have no dissipation, I have a Hamiltonian. There's some anti-unitary operator t, right, that encodes our time reversal symmetry. But even classically, as soon as I think about an open system where I have dissipation, I need to think about time reversal symmetry a little bit differently, right? If I have a damped harmonic oscillator, right, the motion damps away, playing the movie backwards is not the same, right? So classically, I would say the most useful formulation of time reversal symmetry is the notion of detailed balance. Okay, so this is all classical. Imagine I have a classical, let's call it a stochastic system, that's described by a classical master equation. So let's imagine I have a particle. Classically, it could be living on any of these three states. It could make transitions from one state or one site to another. There are probabilities associated with each of the sites. And you might imagine this kind of rate equation dynamics. How do these probabilities change in time? Where there are transition rates, if you start on one site, you could end up in another site. Okay, so this is like a classical master equation or rate equation. I can think about finding a steady state of these equations, right? Some probabilities that don't change as a function of time. Classical detailed balance is saying, oh, your steady state probabilities, not only are they steady state, they don't change in time, but they satisfy this set of, let's call them local constraints. If I pick a pair of two states, the probability flux across this bond is 0. So this is like the flux going from I to J. This is the flux going from J to I. They're exactly the same thing. Okay, so classically, this is well understood. This is important. This is useful. Classically, if you have this kind of detailed balance, it also means there's a correlation function. If you're in your steady state and you ask about how two different quantities, let's call them A and B, fluctuate, look at these correlation functions. Whether you measure A later than B or vice versa, you get the same thing. And that's known as Onsager symmetry. Okay, so that's something we know and love in the classical context. How do we generalize this to something quantum mechanically? And then the last thing I would say, okay, just classically, if you have detailed balance, it's very, very easy to find the steady state. Because you can use this constraint that for any pair of states, this probability flux has to vanish. I can just directly use that to build up the steady state probabilities. Okay, so classically, time reversal becomes detailed balance. Detailed balance, but lots of constraints on the steady state that we can use to find what the steady state is. How do I do that for a kind of quantum master equation like this Lindblad equation, where I don't just have these incoherent transition rates? Okay, and so this is something where there's a whole community in sort of mathematical physics that spends time coming up with definitions of detailed balance and quantum detailed balance. The definition can never be wrong, right? It can be unhelpful. So I'm going to give you a formulation of detailed balance that at first glance will seem crazy, right? This is not the most obvious way to generalize those classical ideas I just told you about. But this notion turns out to be operationally useful. It lets us get those exact solutions. Okay, so here is my construction, and this is related to what I'm describing as hidden time reversal symmetry. So here is my very reduced schematic of the original master equation. There's a system, I'm calling it A, there's driving and dissipation. that Lindblad master equation, let's say, has some steady state. Okay, and I can diagonalize that steady state. I have these states n and these probabilities pn. And so now my question is, does this system have hidden time reversal symmetry? Right? So you think, aha, it has some time reversal symmetry, and that corresponds to some anti-unitary operator T. Okay, so here is my test. You take this steady state density matrix, you construct a purification of this density matrix. So that means you introduce a fictitious system B, right? You entangle it with system A in just the right way. So now I take this state psi and I trace out B, I get back this steady state density matrix. But the way I'm going to construct this purification is very particular. I'm putting in your guess of what is the time reversal operator on the B system. And for the experts, this has the form of a thermofield double state. Okay, so you guess what T was, we construct this state. So now what is the test? Is this actually a symmetry or not? The test is, let's now take the fictitious system B and the state seriously. So here's my original system. Here is this fictitious system B. I prepared the joint system A plus B in this entangled state. And then I let the system evolve. And how does it evolve? A evolves according to the original Lindblad master equation. B has no dynamics whatsoever. Okay, all of this is a test. This is like a theoretical test to see, did you pick the right T? Does even a T exist? So now, how do I know that I have a symmetry that depicts correctly? Now in this dynamics, I could look at correlation functions. I could measure something on the physical system A, measure something on the fictitious system B, that's this XA of T, YB of 0, or do it the other way around. Right? Measure Y at some time T on the real system A, or the other way around. And so now my definition of quantum detailed balance, hidden time reversal symmetry, if these correlation functions are always the same, we think of this as like almost T has gone to minus T, right? Because the T is on X, the T is on Y here. So this is a funny extended version of Onsager symmetry. If this correlation function symmetry holds for the double system, then I am going to say, aha, your system has hidden time reversal symmetry, right? And it's this operator T that went into the construction here that describes the symmetry. Okay, and so it's hidden time reversal symmetry because it looks like to see this symmetry, you got to look at this construction when you create this doubled system. Okay, and again, this does not seem like the easiest way to generalize the classical construction. Okay, there's a more formal definition of this, and I'm not going to, already behind time, someone's going to ask me about that. This again is the, the little cartoon of what the construction is. And again, this is just one of many, many definitions of detailed balance that exist in the mathematical physics community. It's sometimes confusingly called the KMS definition of detailed balance, okay, but names are not so. So what can I tell you about this funny definition? First of all, it's going to show up in real physical systems of interest, including those 3 classes I showed you a few slides ago. This form of detailed balance can hold even if you have an interesting non-equilibrium steady state. So even if the steady state of the dynamics doesn't commute with the Hamiltonian, you can still have this symmetry. Okay? There are observable consequences. So often at this stage, some experimentalists get mad. You show these really complicated systems, then you say double it, make a copy of it. Like that sounds like madness. This symmetry has observable consequences, even if you don't want to double your system. You want to double your system, that's great. There's even more stuff you can do. And there's also some stuff that we're only starting to sort of understand now and play with, and I don't have time to get into it. This definition is related to something that's well known in quantum information theory, the Petz recovery map that shows up in error correction. It's also surprisingly related to sort of quantum metrology ideas that are based on time reversal. Those are like fun topics, the topic of this course. What I want to this Teaching too much this quarter. It's
We'll be back next week
yeah.
and the week after.
I have like 3 hours. Like my normal the thing I want to tell you about is this funny definition of having time reversal symmetry is related to getting exact solutions. Okay, and how does that work? At first glance, that doesn't seem obvious. Here's a kind of formal way of sort of showing how things work. Remember, classically, if you have detailed balance for a classical master equation, it gives you a lot more local constraints on what the steady state probability distribution needs to be. So something similar happens in this quantum case. If I have this hidden time reversal symmetry, then there's a really nice way of finding the steady state. So if you can find an anti-linear operator that has these properties, it turns each, let's call it jump operator, into its dagger. It turns the non-Hermitian Hamiltonian, if I combine this H with the Z dagger Z, into its dagger. Then you're guaranteed that that anti-linear operator is basically the square root of your steady state density. Okay, so this is now, you can believe me on this, this makes the problem easier. If you think you have this hidden time reversal symmetry, don't try to find the steady state directly. Try to find this operator psi that has all these constraints. Okay, so that's very formal. Here's a much more physical way of thinking about why this symmetry gives us a neat trick for finding exact solutions. So here again is a cartoon of my original driven system. Let's just take the dissipation to be photon loss. So photons are leaking out of this, let's call it a cavity with some unknown complicated dynamics, some rate kappa 1. I want to know the steady state. So you can't stop me from modeling the dissipation as a chiral waveguide. So when the photons leak out, they go into this waveguide, they go off to infinity, right? They never come back, so fine, I can model it like that. And then what can I do? I could imagine putting a second fictitious system, right, downstream in such a way that it catches everything with the original system amiss. Okay, now I could do that, I could do this magic, then this entire composite system would relax to a pure state. If I have that pure state, I would just trace out the fictitious system that gives me what I want. Okay, so in general, this is not very helpful because what the hell do you put downstream that is going to magically catch, everything? Well, if you know that you have this hidden time reversal symmetry, there's something very simple to put downstream. You just basically put a copy of the original system, but the Hamiltonian goes to -8. Okay, so this is something that was first exploited for a particular problem in this nice paper from Peter Zoller's group. This is actually something that's much more general. It's related to this notion of hidden time reversal symmetry. It's something that even works in kind of many-body settings. Okay, and if you didn't like the discussion of like time reversal symmetry, etc., you could even just think about this cartoon here. How are we going to find exact solutions? We're trying to understand this system. We're going to try this trick, model the dissipation with these chiral waveguides, put a copy of the system downstream, and ask, can we get a pure steady state? Any questions? Otherwise, I'm going to try to show these ideas in action and actually use it to understand some of these systems. John?
The second system is only absorbing particles. Doesn't this say something physically deep about the system? That one's absorbing particles, the other one should be emitting them. So if in a steady state this thing's emitting particles, doesn't the other one end up with an infinite number of particles?
So okay, so two things here it's in the cartoons. When I say I copy the original system, the fictitious system is also
coherently taking it back.
Yeah. And again, the fact that this works is, seems like it kind of works. Yeah, well, it works when it works, and it is related to the first thing. Like, is there a notion of hidden time reversal symmetry? Is there a quantum detail balance? Like, so the existence of this, sometimes people call this perfect absorbers, is directly related to the fact that the original system has a meaningful notion of time reversal. Okay, so let's make this a bit more concrete, right? And like actually get some physics out of this, right? So let's turn to one of the models that I brought up. So this model of, let's think of it as like a dissipative transverse field Ising model, this model that is related to the experimental von Berle's group. So what do I have? I have a collection of two-level atoms or qubits. Let's take the interactions to be all-to-all. So these are all-to-all Ising interactions. And then every qubit is subject to a Rabi drive. And again, I'm working in the rotating frame. So delta is the detuning of these Rabi drives. The amplitude of the Rabi drive, omega j, is varying from qubit to qubit. And then I'm going to balance this by saying, okay, there's losses, there's spontaneous emission. So the full master equation, here's the Hamiltonian dynamics. This is telling me I have single qubit losses, right? T1 processes at some rate gamma. And then maybe I also have some collective superradiant decay. So this big S minus is like the sum of all of the single qubit lowering operators, right? This is saying that there could be some coherence in how these qubits kind of decay. And as I think I already mentioned, this is relevant to different experiments, right? There have been many, many recent sort of approximate theoretical studies of this model in different regimes. Field theory tells you this can have phase transitions. Just to emphasize, even though, look, it's an all-to-all interaction, it's not trivial. It's not necessarily trivial. So first of all, we're not necessarily going to be in the limit where the number of qubits goes to infinity. And also, this is not a fully collective problem. So I could write this term just in terms of the total big SZ, right? Sum up all of the qubit sigma zs. But then this term here breaks the collective nature of the problem, right? Every qubit could be seeing a different drive amplitude. This model doesn't have any collective symmetry or any permutation symmetry. So even numerically being able to simulate this, the fact that there's no permutation symmetry makes things difficult. Okay, and so miraculously, this is a model where there is a notion of hidden time reversal symmetry. We can analytically find the steady state of this master equation. Okay, and just because it's so beautiful and compact, I'm going to write it down. Right, often like these exact solution techniques get a bad name because there's an exact solution, but no one wants to show it to you because it's so horrible to look at, and you need to spend your whole career being able to do something to get physics out of the exact solutions. For a lot of these models, that's not the case. So the exact solution, the steady state density matrix of all these qubits, this psi is kind of like the square root of that steady state density matrix. And it's actually really, really simple. So this is just a fancy way of writing a generalized binomial series. So this psi is just a power series, right? In this operator here, this is just a weighted sum of each qubit's lowering operator. And you see that the coefficients here are in with the size of the driving. Okay, let's not worry about these factors here. So in the limit where the drives are enormous, this psi is just 1, psi dagger is 1. The density matrix is just fully mixed. It's an infinite temperature state. The drives have just completely heated you up to infinite temperature. This is now telling you, oh, if the driving is not infinite, what are the corrections to having an infinite temperature state? Okay, so it's an exact description of the steady state of this. You can really use this form now to kind of calculate whatever you want. So you want to calculate some crazy multi-qubit correlation function. There's analytic expressions for that that come from this expression here. And again, to emphasize, not a fully collective or symmetric problem. Every qubit could have a different driving amplitude. There is single spin relaxation here. Okay, and so what's the kind of physics that comes out of this? One thing I always think is fun is you can really understand how a dissipative phase transition emerges in the system as you increase the number of qubits. Okay, so what this is showing is the average density of excitations, right? Each qubit could be in the ground state or the excited state. If it's in the excited state, I call that an excitation. So this is the average density for some fixed drive amplitude in units of this scaled interaction for some value of the dissipation. As I tune the detuning of the drive, you can think of that as a chemical potential. And so what do you see? This light red curve is if I just have 4 qubits. You see that, okay, as I come closer to resonance, there's this peak, there's this wiggle. I see kind of resonances that you might assume are related to the eigenstates of the many-body Hamiltonian. As you start to crank up the number of qubits, these discrete resonances, these peaks, they get closer and closer together. And when you get up to 128 qubits, you really have what looks like a first-order phase transition. Okay, so the exact solution really lets you understand the emergence of sort of phase transition physics in this system. Again, this also works if the system is disordered, right? So it works in a regime where you couldn't do numerics in a simple way. And even in the regime where you might go, oh, look, this first-order phase transition, can't I just get that from mean field theory? Right? Is there any reason to the exact solution? So if you do mean field theory, this is this dashed curve that you would get. You would find that there are regimes of the tuning where you have multi-stability. It looks like there's multiple solutions. Okay? So then the question is, well, where is the phase transition? In mean field theory gives me 3 solutions. So some people might say, oh, it's at the onset of bistability over here. Some people might remember their, thermal physics or whatever, 301 and go, there's this thing, equal areas, Maxwell construction. I should draw a line that this area is equal to this area. That's this blue line here. Neither of those really tell you where the transition is. Because what it's telling you is there's something non-equilibrium that influences the nature of this transition, even in the limit where n has gone to infinity. That's something that's captured in the exact solution. Okay, and then this is just a prettier picture of the full phase diagram of this model. This is varying the tuning. This is varying the drive amplitude. The color scale is the density of excitations, right? There's a high density phase, there's a low density phase. There's a line here of first order phase transitions. Mean field theory gives you bistability in this entire lined area. And then the Maxwell construction, right? What's the cheapest way of trying to predict the first order transition? That fails to work. Okay, so there's a lot of so it's not just, hey, great, we have an exact solution, give me a gold star. We can actually get some physics out of these exact solutions. Okay, and then I did mention that this hidden time reversal symmetry, right? You can actually measure something and see that the symmetry exists, right? And that measuring something is not confirmed that my exact solution is correct, right? That would really be the easiest way to verify a symmetry. So what you can do if you have hidden time reversal symmetry, certain correlation functions for the actual physical system need to be time symmetric. Okay, so for this system, and this is now my case where I just have 5 spins, all of these drive amplitudes are essentially random. I can imagine looking at, let's call these pairing correlators, right? So these are 2 spin lowering operating for qubit 1 and qubit 2. Either I measure the qubit 1 thing later, or I measure the qubit 2 thing later. And what this blue curve is showing is there's supposed to be a dashed curve and a solid curve, they're identical. So these pair of correlation functions are the same. They obey an Onsager symmetry. I can break the symmetry, the hidden time reversal symmetry, by doing something very innocuous. I just add some heating dissipation to each qubit. There's some process where each qubit can incoherently go from ground to excited. And that innocuous thing breaks the hidden time reversal symmetry, because I can't give you an exact solution anymore. But now you see, we go down to a modest temperature, these 2 correlation functions are no longer the same. Okay, so the fact that the symmetry exists or doesn't exist, there is something very direct that you can measure. Okay, so I am, as always, taking more time than I expected. I wanted to tell you something about a bosonic model, which is we're talking about spins. Maybe I'm going to stick to the sort of theme of spins and just end with a really recent application of these ideas to a spin model that is definitely not all-to-all interactions and not describable in field theory. Okay, so avert your eyes for a moment. If I just zip through lots of interesting stuff, you didn't see that. So you might still be like, look, you solved some all-to-all Ising model, fine. Can you solve something where the interactions are more local? So let's go to a model where there really is no global interactions at all. let's go to a model and let's just focus on this last one here. What if I have a 1D chain of qubits, right? Where without the driving dissipation, I have just popping of excitation, so these XY interactions. That by itself would correspond to 3 fermions, right? But then I add this ZZ interaction, right? So it's like a nearest neighbor repulsion or attraction between the qubits. So this XXZ model now corresponds to an interacting fermionic model, right? This is an interesting integrable model. So if I just had the Hamiltonian system, there are beta ansatz techniques that let you say things about this. But we're going to make life interesting. We're going to add some driving and we're going to add some dissipation. And I'm not going to do that uniformly on the system. I'm going to add driving just on the very first side of the chain. In the usual way, I'm going to add a term of the Hamiltonian that is a sigma x just on the first site. The drive stuff is omega. And on the last site, I'm going to put my Himblad dissipation. There's going to be a rate gamma at which excitations can just leave that last qubit. Okay? And so this, again, so here in an even bigger way is a picture of our model with the driving term. Here's the master equation with the dissipation. There's been an explosion of interest in like non-equilibrium properties of these XXZ spin chains, both because people have done experiments and pulled atoms in superconducting circuits, but it's also a really amazing playground for looking at non-equilibrium quantum physics and non-equilibrium quantum transport. Right? Naively, you would expect, oh, look, if I drive this site here, particles only leave at the end, I could get a current through this system in a steady state. What are the properties of that current? How does it scale as I make the system size bigger and bigger? Okay, and so here we have a bit of a wrinkle on the kind of models that people have typically studied in this setting. The driving is coherent. The driving is a term in the Hamiltonian. The dissipation is dissipation, right? That's a term in the dissipator. Okay, and so the kind of a really interesting thing is this is also a model that's exactly solvable with these hidden time reversal symmetry. Okay, there is a hidden time reversal symmetry here that lets us write down an analytic description of the steady state. Okay, and just really briefly, how do we solve it? There's this idea of constructing a perfect absorber. That's one way of thinking about the exact solution. So here is the original spin chain. There's only dissipation on site N. We'll model that dissipation with this, let's call it a chiral waveguide. So the qubit excitation turns into a photon. The photon can only go from top to bottom, never comes back. So to get a solution, I imagine coupling another spin chain with exactly the same Hamiltonian parameters, except they have minus signs, downstream along this waveguide. Okay, so if I call this HA, this is like the B chain has minus the Hamiltonian of the A chain. And now the idea is, okay, this composite system, the two chains, this dissipation along the boundary, that actually relaxes into a pure steady state. And that pure steady state, I won't go into that, the exact solution has the form of an infinite dimensional matrix product state where you know all of the matrices. Okay, and for, there's a connection to a very, very famous model in statistical physics, the asymmetric simple exclusion process. So classical physicists are also very interested in non-equilibrium situations where particles hop on a chain, there's interactions. Funnily enough, this solution for a quantum model has some formal connections to that. Okay, so cool. There's something you could do an experiment on. There's an exact solution here. What do we learn from it? So this model also has really, really surprising phase transition physics. So like that all-to-all Ising model I talked about, what I'm looking at here is what I want. We're looking at like the average density of excitations in this chain. As I vary the drive amplitude, and again, the drive amplitude is just on the first site. And as I vary, that interaction field. So delta now is not into tuning. Delta is the anisotropy in this spin chain, where if you want, it's the ZZ interaction, right, between adjacent sites. Okay, and so what you see, and again, the color scale There's a high density regime, there's a low density regime. You see that there are different low density and high density regimes here, right? So the most obvious thing is that when delta over J crosses 1, you go from high density to low density. That transition is not so surprising. That transition is a property already of just the Hamiltonian without the coherent driving. Okay, so that's well known that you go from some Luttinger liquid state to some kind of antiferromagnetic state there. So this is a transition that you could have already expected from the physics of the closed system. In contrast, if I take a delta that's less than 1, and I go from left to right, just increase the drive, this transition from low density to high density, that has no correspondence to something in a closed system. Okay, so we have a kind of, phase transition in the density that occurs at some critical value of the drive. That critical value of the drive is sort of the hopping with the interaction kind of subtracted off. This all comes out of the exact solution. Okay, one of the fun things with the exact solution, this is for 100 qubits. I challenge you to do 100 qubits with this system on QTIP, right? I also challenge you to do 500 or 800 or 1,000, right? So with the exact solution, this is all more than tractable. So for example, we can take this kind of density data as a function of the detuning. I just got the detuning, the drive amplitude is scaled differently. And we get some kind of beautiful finite size scaling collapse. Okay, so again, this is just to give you a flavor of what's coming out of this, a really different kind of system, an interacting quantum spin chain. The exact solution lets us identify for the first time this surprising kind of dissipative phase transition. It also really lets us understand the exact things about its properties. Okay. And then time is getting short. The last thing I will say, I think it's the last thing, I don't know what the next slide is. This trick that we use to get a solution, right? So I want to solve this spin chain here. I make a copy. I couple it to this chiral waveguide at the edge, right? That is something you could build in the lab. I couldn't build it. Someone in the room could probably build it. And if you could, that's really cool, because now what's the exact solution telling us? So here are 2 chains of qubits. They're coupled to the same waveguide at the edge. The first qubit of each chain is driven. Our exact solution is saying this entire many-body system will relax into a pure state. Okay? And that pure state will have non-trivial entanglement, no matter how you cut your system into A and B. But even weirder, this pure state that we get will carry a current. So in this pure steady state, there will be a current going in one direction along A, coming back in the opposite direction in panel B. And it's even weirder when you think, why does this exact solution exist? It exists because there's a notion of quantum detailed balance in this system. And the cartoon version of classical detailed balance is in your steady state, there are no currents. Okay, so this is just telling you that quantum detailed balance is a stranger beast. It shows up in models of interest. It's even compatible with steady states that carry current. Okay, so okay, what's my last slide? So I didn't remember there was nothing after that. I'm just going to flash up my conclusions. Hopefully this wasn't too heavy a talk after lunch, right? I gave you some sense of there's a surprising way of getting exact insights into a class of very different looking, complicated looking, dissipative many-body systems. And those exact solutions are related to a notion of time reversal symmetry of these open systems. Right? And it suggests that there's a very particular way of how to think about and define time reversal in this open quantum system setting. That could be something that's useful far beyond this task of just trying to get exact solutions. So with that, I will stop. Thank you.
John seems so.
Only one question. I know you well enough, for too long.
Yeah. I guess we should probably start with Henry, right? Because I know I'm intellectually a student, but Henry's actually a student.
Okay. So you you showed these exact solutions. You talked about getting a version of detailed balance for these systems. Obviously, when you have a classical system and you don't have an analytic solution, detailed balance still like opens the door to like pseudodynamics, like Metropolis algorithm, which means, you know, I can very efficiently simulate the system to find steady states. Is there some similar pseudodynamics I can do for these hidden time reversal symmetry systems?
Yeah, that's a really good question and insight, and that's something we're thinking about. So here, we're saying, okay, like sometimes you have this hidden time reversal symmetry, and then if I have that on top of that, I can use it to get an analytic steady state. But you can back away and say, maybe if I have this symmetry, there's a much more efficient numerical way of getting a steady state. So that is something we've started to think about. I don't know if we've thought about it in pseudodynamics, but maybe that's a good idea. But the idea is if you assume this symmetry, but don't say that also I'm going to do some crazy infinite dimensional NPS on that. Let me just use that numerically to have a more efficient way of finding the steady state. We think that that should yield insight. So that's work in progress.
Okay. So you've got these exact solutions to like pretty hard looking problems. But as soon as you break these the model, it seems like what I'm wondering is there some sense of a perturbation to around this?
Yeah, and that also kind of works in progress in the same way that for like closed system integrable systems, you weakly break integrability. You can do kind of a perturbative treatment of that. There is a similar approach one can try to do for it, right? And we've done so one of the simplest systems that has this is the kind of system that people are looking at for bosonic error correction in superconducting circuits, a single cavity with a 2-photon drive and care. There you can add terms that break the symmetry. And it seems like there is a perturbative way. So use the exact solution and say things about what happens in this wider parameter space. But yeah, that's definitely a good idea and something I think you can do here. You're welcome to do it too. I'm looking for postdoc, right? So maybe.
Yeah, so do you expect that this hidden time reversal symmetry is present in generic systems or that it's...
Yeah, and I think always like, you know, you want to be optimistic and show all the successes. If you just come to me with some random Hamiltonian and Rublat jump operators, almost certainly will not have symmetry, right? So, and I think I even showed you that in this, in this example here, if you just see that at temperature, if the qubits now can get excited, the symmetry is gone, right? So one of the things I don't have any good rule of thumb of understanding what kinds of systems have this symmetry, what kinds of systems don't, right? That's why we put the word hidden there, because it's not some obvious property where I just look at this cartoon and go, oh yeah, this is going to work. They're very innocuous terms you can add that destroy the symmetry. You can't get a solution. There are crazy terms you can add that are compatible with it. So it's a really interesting question. We don't really have a great answer in terms of when do you have this symmetry. We know there's a bunch of models that have it. That makes us happy, but yeah, it'd be nice to understand that better.
So in particular, in the local version of the transverse field Ising model, does it hold?
No. So if you, like that transverse field Ising model, if these couplings are, we've looked at like simple things, like if you really just made the nearest neighbor on some like 2D lattice, this symmetry is lost. Could you come up with some pattern of J's that encodes some spatial structure that still allows an exact solution? That's an interesting question. There aren't integrable models without dissipation where you really have to pick the constants in a very particular way to get a solution. It wouldn't surprise me if I picked all of the J's in just the right way, I could get an exact solution and still have a notion that distant qubits don't talk to one another. But yeah, that's also something to look at.
I was wondering, are there, as you show this technique with, you know, a Hamiltonian, and then I sort of convert the Hamiltonian and drug. Are there can I leverage like other symmetries in a Hamiltonian where instead of inverting the Hamiltonian, I apply some other transformation on the sort of pair system?
So I think you can get things still to work. It's like H and minus H for this kind of absorber, right? It's all morally equivalent. Like it's H and, you know, minus H prime, where I've just made some unitary transformation between the two Hamiltonians. There's a little bit more freedom to get these perfect absorbers to work. That I don't think is super, a little bit useful for these exact solutions. There are ideas that these perfect absorbers could also be like, maybe not perfect, but very, very good quantum tensors. That the fragility of these solutions actually is really great for like parameter estimations, right? In that context, having something more general for the minus H could be a real advantage.
Okay, so at the end there, you were looking at an XXZ model, which when you put delta to 0 is supposed to have a BKT transition, which I guess would have been at the bottom of your plot here. Did you find anything interesting with the driven-dissipative version of that, or?
Go back for a second. So when delta is 0, this model, even with the dissipation, becomes equivalent to free fermions, right? And so in that case, we know what we should get what we should get. There's also something very weird that if you really look at this, like I'm ignoring some important structure in this plot. So I'm focusing on this green line and say there's this, but there are also weird spiky things that kind of come out. So delta equals 0, the system is free fermions. It turns out there's some weird quantized values of delta that correspond to these spikes, where some of that free fermion nature still seems to exist. And I don't fully understand that, but it's there in the exact solution. Like it tells you what those values are. I don't know what the physics is. Yeah.
Some sort of fractionalization thing or something.
Yeah, that would be nice, but yeah. Or are we?
Yeah, I think maybe just one more question. So,
can I comment on the superficial similarity between your fictitious P system and the parity time symmetric system? Assuming this your A system is the first one and P is the symmetric part of it. And you think that this super hidden time reversal symmetry exists in the kind of the collective PD symmetry that we predict?
Yeah, I don't think there's like a really useful connection the way people think about PT symmetry. This is also a completely many-body technique. But one thing I will just briefly say, right, is that if you look at these equations that are what holds if you have in time reversal symmetry, this is somewhat reminiscent of the notion of pseudo-hermeticity, which you could think of as like a generalized version of PT symmetry. So look, H is not Hermitian, but H and H dagger are similar. So this is not the same thing because psi is an anti-linear operator, but I don't know if there's more to make of that connection. I'd say this is the closest that we can get to something that reminds you of things you think about when you think about PT symmetric systems.
The lowest level level. Photonic. It looks oddly like it didn't show the